Welcome back to the deep dive.
Yeah.
This time we're
Always exciting to be back.
taking you on a journey into deep learning.
Right.
You've sent us some really fascinating material,
Yeah.
excerpts from Ian Goodfellow's deep learning book,
Of course. Yeah.
and a paper called Optimization for Training Deep Models.
A classic.
Sounds pretty dense, right?
Yeah, it can be a bit intimidating.
And don't worry, we'll make sure you get the most out of these.
Absolutely.
Even if they seem a bit intimidating at first glance.
Yeah, we're here to break it all down.
Hey.
Make it clear.
Let's just jump right in.
Right. Yeah.
First things first, what exactly is deep learning?
That's the question. Right.
How is it different from, say, just plain old machine learning?
Yeah, that's a great question. It's actually a specialized subset of machine learning.
Okay.
And at its core, machine learning is all about algorithms that allow computers to learn from data.
Okay.
The book you shared actually gives a classic definition. A computer program is said to learn from experience E with respect to some class of tasks, T in performance measure P, if its performance at tasks in T, as measured by P, improves with experience E.
Oh, wow.
That's a mouthful.
So that's the learning part. But what kind of tasks are we talking about when it comes to deep learning?
Right, so think about things like
Like what?
recognizing images, understanding and translating languages, even generating captions for images.
Yeah.
It's not just about number crunching.
Okay.
Deep learning can even tackle structured output tasks, where the result is something more complex,
Okay.
like a sentence describing a picture.
Now that you mention it, I've seen those image captioning tools online.
Yeah, they're everywhere.
It's really impressive how they
Right.
can analyze a picture and describe what's happening.
Yeah, and it's all thanks to these neural networks.
Ah, neural networks.
Yeah.
So are we essentially trying to create artificial brains here?
Not exactly.
Okay.
It's more about capturing some of the core principles of how brains process information,
Right.
not about perfectly mimicking them.
Gotcha.
You know, a classic example that highlights this is the XOR problem.
XOR.
Yeah.
Remind me what that is again.
It stands for exclusive OR.
Okay.
Essentially, it means one or the other, but not both.
Okay.
Like a light switch, it's either on or off, but not both at the same time.
Okay. Got it.
And a simple neural network with even just one hidden layer can solve this problem easily.
Interesting. What makes neural networks so good at solving something like XOR that other models can't handle?
Yeah, it really comes down to their ability to learn nonlinear relationships.
Okay.
That hidden layer acts like a switch, allowing the network to capture more complex patterns in the data.
Okay.
And this is where we start getting into the concept of representation learning,
Okay. Representation learning.
which is really what deep learning is all about.
The book you shared seems to emphasize this a lot.
It's a big deal. It really is central to the whole field.
Okay. So what's that all about?
Well, in that XOR example,
Uh-huh.
that simple network was essentially learning a new way to represent the data that made the problem solvable.
Okay.
It's like translating a language.
Uh-huh.
Deep learning models, especially deep ones with many layers,
Yeah.
they can transform data into a form that makes it much easier to analyze and understand.
So it's finding a way to make the data more meaningful to the computer.
Exactly. You can even think about a simple example like PCA,
PCA.
principal component analysis.
Okay.
It's a way to represent data using fewer dimensions
Okay.
while still keeping the most important information.
Gotcha.
Deep learning takes this idea to a whole new level,
Okay.
learning far more intricate representations.
I'm starting to see how powerful this can be, but I have to imagine there's some serious challenges too, right?
You're absolutely right. One of the biggest is what's often called the curse of dimensionality.
Ooh, the curse of dimensionality.
Yeah, so as we deal with more complex data with lots of features, the number of possible variations explodes.
Okay.
Think about a simple checkerboard, right? Learning a pattern on a standard checkerboard is fairly easy.
Okay.
Now imagine adding more and more dimensions to that checkerboard.
Okay.
It quickly becomes impossible to keep up with all the possibilities.
I'm getting a headache just thinking about that.
Yeah, it gets complicated quickly.
So how does deep learning tackle this curse?
That's where things get really fascinating.
Okay.
Deep learning has sort of a secret weapon. Priors.
Priors.
Yeah, these are assumptions baked into the model itself.
Okay, so these priors help narrow things down.
Precisely. One common prior is the smoothness prior.
Okay.
This means the model assumes that similar inputs should generally have similar outputs.
Okay.
However, for the really complex tasks deep learning tackles, this alone isn't enough.
Right.
That's why deep learning shines.
Okay.
It goes beyond these simple priors by learning richer, more nuanced representations, layer by layer.
So it's like building up a complex understanding
Exactly.
by starting with simpler concepts and combining them.
Yeah, almost like how we humans learn.
Interesting.
But the question then becomes, how do we actually teach these deep networks?
Right. We need to train them
Right.
to do what we want them to do. What's involved in that?
Well, at its core,
Okay.
training is about finding the right parameters.
Okay.
These are like the settings knobs that control how the network behaves.
Okay.
A classic algorithm for this is called gradient descent.
Gradient descent. Okay.
Imagine a ball rolling down a hill.
Okay.
It's trying to find the lowest point, which in this case represents the least amount of error.
I can picture that, but the material you shared
Huh.
mentioned some challenges with gradient descent, right? It's not always a smooth ride down that hill.
Exactly. Sometimes the ball might get stuck in a rut, or it might overshoot the target.
Right.
We run into things like vanishing gradients,
Uh-huh.
where the signal gets weaker and weaker as it travels through the network,
Okay.
or saddle points where the algorithm can get trapped.
Hmm.
And sometimes the mathematical landscape itself can be very tricky to navigate,
Right.
making it hard to find the best solution.
So it's not just about finding any solution.
Right.
It's about finding a good one.
Exactly.
And efficient.
And efficiently, yeah.
I see why this optimization part is so important.
Absolutely crucial.
So how do we make sure our deep learning models are well trained and avoid these pitfalls?
Well, that's where things get really interesting.
Okay.
There are lots of clever techniques to improve the training process.
Like what?
One you'll encounter is called momentum. Think about that ball rolling down the hill again.
Uh-huh.
Momentum gives it an extra push,
Okay.
helping it overcome small bumps and accelerate towards the solution.
So it's adding a bit of oomph to the learning process.
Exactly. It's
Yeah.
giving it that extra boost.
I like it. Are there other techniques like this?
Absolutely.
Oh,
There's Nesterov momentum, which is like taking a test run before committing to the full move.
okay.
And then there's initialization.
Right.
It's not just about starting somewhere. It's about starting in the right place.
Right.
A good starting point can make a huge difference in how quickly and effectively the model learns.
Okay. That makes sense.
It's like choosing a good starting point for a hike,
Right.
rather than starting miles away from the trailhead.
Yeah.
And before we move on to some of the more specialized types of deep learning models,
Okay.
there's one more important concept to cover: batch normalization.
Batch normalization.
Yeah, it's not an optimization algorithm itself,
Okay.
but it can really help stabilize training
Okay.
and allow for deeper networks.
Okay. Break that down for me.
Think of it as standardizing the data flow between the layers of the network.
Okay.
This prevents extreme values from disrupting the learning process
Okay.
and makes it easier for the model to converge to a good solution.
Okay.
It's like having a quality control check to ensure everything is running smoothly.
Quality control for deep learning. I like that.
Yeah,
So we've covered the basics of deep learning.
the foundation,
These neural networks
the building blocks.
and some of the challenges in training them.
It's a journey.
Now, what about the different types of deep learning models we hear about?
Right, we got to talk about those.
Where do those fit in?
That's where we're heading next.
Okay, let's do it.
You've probably heard of things like convolutional neural networks, or CNNs,
Yeah.
and recurrent neural networks, or RNNs.
Yeah, I've heard those.
These are specialized architectures designed to handle different types of data and tasks.
Okay, sounds exciting.
It is.
Let's dive into those next.
Let's go. They're like specialized tools, right?
Okay.
Designed for specific jobs.
Okay.
CNNs are particularly amazing at working with images.
I've definitely heard of CNNs.
Yeah.
Something about how they're used in facial recognition technology.
Right, exactly.
But how do they actually work?
So they have a unique structure
Okay.
that takes advantage of the way images are laid out,
Okay.
with pixels arranged in a grid.
Uh-huh.
CNNs use these things called convolutional filters
Okay.
that scan across the image,
Uh-huh.
looking for patterns,
Okay.
like edges, corners, textures.
So they're kind of like super-powered pattern detectors.
Exactly.
Yeah.
And they do this by looking at small patches of the image at a time,
Okay.
which makes them incredibly efficient.
Okay.
It's not just about recognizing individual pixels.
Right.
It's about understanding the relationships between them.
That makes sense.
It's like how our brains don't just see a bunch of dots.
Right.
We see shapes, objects, and scenes.
Yeah, exactly.
And CNNs have three key ideas that make them so powerful.
Okay, what are they?
First, there's sparse interactions,
Okay.
which means each unit in the network only connects to a small group of its inputs.
Okay.
This helps make the network more efficient
Okay.
and reduces the number of parameters we need to worry about.
So it's like focusing on the most relevant connections.
Exactly.
Right.
Rather than trying to connect everything to everything else.
Gotcha. What's the second one?
Then we have parameter sharing, which means the same set of weights gets used across different parts of the image.
Okay.
This makes the network more robust and less prone to overfitting
Okay.
because it's learning general patterns,
Okay.
not just memorizing specific pixel arrangements.
Ah, so it's like learning a set of rules that can be applied anywhere in the image.
Exactly.
Okay.
Not just in one specific spot.
What's the third idea?
The third one is equivariant representations.
Okay.
It means that if you shift the image,
Uh-huh.
the network's response shifts in the same way.
Okay.
So if you move a picture of a cat to the left,
Okay.
the network still knows it's a cat.
So it's not just about memorizing the exact position of each pixel.
Right.
It's about understanding the underlying features
Exactly.
that make a cat, no matter where it is in the picture.
Yeah, it's pretty impressive.
That is pretty impressive.
And because of these strengths,
Yeah.
CNNs are behind many of the advancements you see in image recognition,
Okay.
object detection, and even self-driving cars.
I can definitely see why they're so important. But what about other types of data,
Right.
like language or time series?
Right.
Do CNNs work for those too?
That's where RNNs come in.
RNNs?
Yeah, they're specifically designed for sequential data.
Okay.
Things like sentences, music, or stock prices,
Okay.
where the order of the elements really matters.
Right, because the meaning of a sentence changes completely
Exactly.
if you rearrange the words.
Totally.
So how do RNNs handle that sequential nature?
They have this really clever feedback loop built in.
Okay.
It's like having a memory
Yeah.
that allows them to keep track of what came before.
Okay.
This lets them understand context
Okay.
and dependencies between elements in the sequence.
So it's like how we understand a story.
Exactly.
We remember the earlier plot points to make sense of what's happening now.
Yeah, that's a great analogy.
And this makes RNNs incredibly powerful
Very powerful.
for tasks like language translation, text generation,
Right.
and even speech recognition.
Yeah, all sorts of things.
I've also heard of these things called LSTMs,
LSTMs, yeah.
long short-term memory networks.
Right.
Are those related to RNNs?
Yes. LSTMs are actually a special type of RNN.
Okay.
Think of them as RNNs with an even better memory.
Okay, so they're like,
They have this internal mechanism that helps them remember important information
okay.
from much earlier in the sequence,
Right.
even if there's a lot of other stuff in between.
So they're like RNNs with a supercharged memory.
Exactly.
Okay.
This makes them incredibly useful for tasks where you need to capture long-term dependencies,
Okay.
like understanding the plot of a novel
Right.
or analyzing trends in financial data over time.
Wow. RNNs and LSTMs sound like incredibly powerful tools
They are.
for understanding language and other sequential data.
Absolutely.
But we've talked a lot about these specialized architectures.
Yeah.
Let's zoom out a bit.
Okay.
What about the bigger picture
Right.
of how these deep learning models are actually implemented?
Yeah, the practical side of things.
Yeah, it can't all be theory, right?
No, you're right.
So what kind of computer do I need to run these deep learning algorithms?
Well, deep learning can be very computationally intensive,
Okay.
especially for complex tasks
Right.
like image recognition or natural language processing.
Mm-hmm.
It involves tons of calculations,
Okay.
and traditional CPUs can struggle to keep up.
Right.
That's where DPUs, or graphics processing units, come in.
GPUs, aren't those mainly used for gaming?
Yeah, originally they were designed for graphics-heavy tasks,
Right.
but it turns out that the same parallel processing power
Okay.
that makes them great for rendering 3D graphics
Uh-huh.
is also perfect for the kinds of calculations deep learning needs.
Okay.
They can handle massive amounts of data simultaneously,
Okay.
speeding up the training process significantly.
So it's like having a supercharged engine for deep learning.
Exactly.
Okay.
GPUs have been absolutely instrumental in the explosion of deep learning research
Right.
and applications we've seen in recent years.
But even with powerful GPUs, there are
Right.
still limitations, right?
Yeah, that's right.
So what's next?
Well, that's why there's a lot of exciting research going on
Okay.
in developing specialized hardware
Okay.
designed specifically for deep learning,
Wow.
like custom chips and circuits.
Dedicated deep learning hardware. That's fascinating.
Yeah, it's pretty cool stuff.
It sounds like a lot of effort is going into making these models faster and more efficient.
It's a big focus, for sure.
But speed isn't everything, right?
Right.
We also need to make sure these models are actually accurate and reliable.
Absolutely.
How do we do that?
That's where the art and science of hyperparameter tuning comes in.
Hyperparameters. Okay, that sounds a little mysterious.
Yeah, it can be a bit of a black art sometimes.
What are they exactly?
Think of them as the settings knobs for your deep learning model.
Okay.
They control things like the learning rate,
Okay.
which determines how big of a step the algorithm takes during training,
Okay.
the number of layers in the network,
Mhm.
and the regularization strength, which helps prevent overfitting.
So if the deep learning model is like a car,
Yeah,
hyperparameters are things like the steering wheel, the gas pedal, and the brakes.
that's a great way to put it.
Okay.
And just like with driving, finding the right settings is crucial
Right.
for getting the best performance out of your model.
But with so many knobs to adjust,
Yeah, it can be overwhelming.
how do we know which settings are best? It can't just be trial and error, can it?
There's definitely some experimentation involved,
Okay.
but it's not just random guessing.
Okay.
There are systematic approaches to hyperparameter tuning.
Okay. Like what?
One common technique is called grid search,
Okay.
where we try out different combinations of hyperparameters
Okay.
and see which one performs the best
Okay.
on a separate set of data that we hold out for testing.
So it's a bit like a scientific experiment.
Exactly.
Okay.
Where you're trying to find the optimal conditions.
Right.
And there are even more sophisticated techniques, like random search and Bayesian optimization.
Wow. That's a mouthful.
Yeah, there are a lot of options.
That can help us find good hyperparameters more efficiently.
Exactly.
Uh.
It's all about finding the best approach for the problem at hand.
This is all starting to make a lot more sense. But we've talked a lot about the technical details of deep learning.
Yeah,
What I'm really curious about are the applications.
right. How is it actually used?
Yeah, what are some of the specific areas where deep learning is making a big impact?
That's a great question.
Yeah.
And the answer is pretty much everywhere.
Okay.
But two of the most exciting and rapidly developing areas
Okay.
are computer vision and natural language processing.
Ah, those sound familiar.
Yeah, we've touched on them a bit already.
So computer vision is all about teaching computers to see, right?
Precisely.
Mm.
It's about giving computers the ability to understand and interpret images and videos
Okay.
in a way that's similar to how humans do.
Okay.
Deep learning has been absolutely revolutionary in this field.
So it's more than just recognizing objects in an image.
Right.
It's about actually extracting meaning
Exactly.
from visual information.
We're talking about things like object detection,
Okay.
where a model can pinpoint the location of different objects in an image.
Okay.
Image segmentation,
Mm-hmm.
where it can divide an image into regions representing different objects
Okay.
or parts of objects.
Okay.
And even image generation,
Wow.
where deep learning models can create entirely new images from scratch.
Image generation from scratch. How is that even possible?
That's where those GANs come in.
Yes.
Generative adversarial networks.
I remember hearing about those.
Yeah, they've been making a lot of headlines lately.
They sound like something out of science fiction.
They're pretty amazing.
So how do they work?
It's actually a pretty brilliant idea.
Okay.
You have two neural networks competing against each other.
Okay.
One network tries to generate realistic images,
Uh-huh.
while the other acts like a detective,
Oh.
trying to spot the fakes.
Oh.
This competition forces both networks to get better and better,
Okay.
leading to incredibly realistic and sophisticated image generation capabilities.
Wow, that's really clever.
A really cool idea.
It's like an arms race, but for creative image generation.
Exactly.
What are some of the real-world applications of this technology?
The applications are pretty mind-blowing.
Okay, like what?
Genes are being used to generate everything from photorealistic portraits
Wow.
to stunning landscapes.
Okay.
They're even being used to create new fashion designs
Oh, way.
and special effects for movies.
So deep learning isn't just about recognizing patterns in existing data.
Right.
It's about creating entirely new patterns, too.
Exactly.
That's amazing.
And this is just scratching the surface
Okay.
of what's possible with deep learning and computer vision.
Okay.
There are so many other exciting areas, like self-driving cars,
Right.
which rely heavily on computer vision to navigate the world,
Uh-huh.
medical image analysis,
Right.
where deep learning is being used to detect diseases and abnormalities in scans,
Wow.
and even facial recognition, which of course
Mhm.
comes with its own set of ethical considerations.
Yeah, that's a whole other conversation we could have.
We could do a whole deep dive on that.
It sounds like deep learning is having a profound impact on computer vision.
It really is.
And as a result, many different industries.
Yeah, it's changing the world.
You mentioned natural language processing is another key area.
Yes, NLP is huge.
Yeah, what's happening there?
Natural language processing, or NLP, is all about enabling computers to understand and process human language.
Okay.
It's a field that's been around for decades,
Right.
but deep learning has really breathed new life into it.
So it's like teaching computers to read, write, and understand us.
Exactly.
Okay.
And it's leading to incredible advancements
Like what?
in areas like machine translation, text summarization,
Okay.
and even those chatbot assistants we all use on our phones and computers.
Chatbots are a great example.
Yeah. Yeah, they're everywhere now.
They seem to be getting better and better
Yeah.
at understanding what we're saying
Yeah, the progress has been amazing.
and responding in a natural way.
They're getting more sophisticated all the time.
It's almost like having a real conversation sometimes.
It really is.
And I know deep learning is a big reason why
Absolutely.
these chatbots are becoming so sophisticated.
Deep learning is powering a lot of the advancements.
They're being used for everything from customer service to education to entertainment.
It's a wide range of applications.
There are even chatbots being developed to provide therapy and companionship.
It's incredible. The possibilities are endless.
Wow. It sounds like we're getting closer and closer to a world where we can interact with computers
Yeah.
in a truly natural way.
It's the dream, right?
Yeah, just like we interact with each other.
Exactly.
That's the goal, but NLP goes far beyond just chatbots.
Right. It's about much more than that.
It's also about enabling computers to analyze and extract meaning
Exactly.
from vast amounts of text data.
Like news articles, scientific papers, social media posts,
Right.
so on.
This can help us understand trends, identify patterns,
Right.
and even predict future events.
It's like having a digital detective
Exactly.
that can sift through mountains of information
Yeah.
and find the most relevant clues.
And it's not just about analysis.
Right.
Deep learning is also being used to generate new text.
Absolutely.
From writing poems to composing music to even translating languages.
It's amazing what these models can do,
With incredible accuracy.
and it's only getting better.
So deep learning isn't just helping computers understand us.
Right.
It's helping them express themselves too.
That's a great way to put it.
The possibilities really are endless.
They truly are.
But as with any powerful technology,
Yeah,
there are also ethical implications to consider.
absolutely. We have to be mindful of that,
We need to make sure deep learning is used responsibly and ethically.
for sure. It's a powerful tool that needs to be used wisely.
But it's clear that this technology has the potential. Absolutely.
To revolutionize so many aspects of our lives.
Already happening.
We've only scratched the surface.
That's right. There's so much more to come.
We haven't even talked about things like reinforcement learning,
Oh yeah, reinforcement learning is a whole other fascinating area.
where agents learn through trial and error,
It's a different paradigm.
or generative models that can create new data, like images and music.
Yeah, we could spend hours talking about generative models.
There's so much more to explore.
Definitely.
But before we get too far ahead of ourselves,
Okay.
let's take a step back
All right.
and focus on some of the key concepts and techniques
Yeah, the foundation.
that underpin all these amazing applications of deep learning.
The building blocks.
We've touched on a few of them already,
We've skimmed the surface.
but I think it would be helpful to go a little deeper.
Okay, let's dive in.
One of the most important concepts in deep learning
Yeah,
is the idea of representation learning,
right. It's fundamental.
which we talked about briefly earlier. We did, but it's worth revisiting.
It's about transforming data into a form
Right.
that's more meaningful and easier for the model to process.
Making it digestible for the model.
But I'm still a bit fuzzy on the details.
Okay, let's break it down.
Can you explain a bit more?
It's really about finding ways to capture the underlying structure of the data,
Okay.
the essence of what makes a cat, or what makes a sentence grammatically correct.
So it's like finding a way to represent the information
Exactly.
in a way that the model can understand.
And these representations can be used for a wide range of tasks,
Okay.
from classification to prediction to generation.
So it's like,
It's like having a universal language
uh-huh.
that deep learning models can speak.
I like that analogy.
It's a good one.
Makes it easier to grasp what's going on.
Glad to hear it.
What are some other key concepts we should understand?
Another important one is the idea of hierarchical learning.
Hierarchical learning.
Yeah,
That sounds a bit like those layers we talked about earlier.
you're on the right track. Hierarchical learning is all about building complex representations
Oh,
from simpler ones,
Okay.
layer by layer.
So like the layers in a neural network.
Exactly.
Okay.
It's like constructing a building, starting with the foundation,
Okay.
and adding layers of complexity on top.
So it's like moving from recognizing individual pixels
Right.
to understanding the entire scene,
Exactly.
building up a richer representation as we go.
And this hierarchical approach allows deep learning models to learn
Yeah.
increasingly abstract and sophisticated representations,
Okay.
capturing the complex relationships within the data.
It's like seeing the forest for the trees,
Precisely.
understanding the bigger picture.
And this brings us to another important concept: inductive bias.
Inductive bias.
Yeah, it sounds a bit technical,
Okay.
but it's a crucial idea.
All right, what is it?
It's about the assumptions that a learning algorithm makes about the data.
Okay.
You can think of it like having a preconceived notion about how the world works,
Okay.
which can be helpful or harmful,
Okay.
depending on whether it aligns with reality.
So it's like having a map
Yeah,
that might be accurate or misleading,
exactly.
depending on whether it reflects the actual terrain.
And deep learning models have a strong inductive bias towards hierarchical representations.
Okay.
They assume that the world is organized in a hierarchical way,
Okay.
which, as we've seen, is often a very effective assumption.
It's like having a map that's designed for navigating complex terrains.
Exactly.
Okay.
With different levels of detail for different areas.
Right.
And this inductive bias is one of the reasons deep learning has been so successful
Okay.
at tackling complex tasks.
It's like having a model that's pre-wired to understand the complexities of the world.
Yeah, that's a great way to put it.
Now let's talk about generalization,
Generalization, right?
which is one of the key goals in machine learning.
Absolutely, it's crucial.
Generalization, I've heard that term before. It's about how well a model can perform on new, unseen data, right?
Exactly. It's not just about memorizing the training data.
Right.
It's about being able to apply what's been learned to new situations.
Okay.
It's like having a student who can ace the test,
Uh-huh.
but can't apply the concepts to real-world problems.
Or a map that's so detailed it only shows one specific route
Precisely.
and can't be used to explore new areas.
And deep learning models, especially when trained on large and diverse data sets,
Yeah.
are surprisingly good at generalization.
Okay.
It's like having a student who's been exposed to a wide range of experiences
Mhm.
and can adapt to new challenges.
So it's about building models that can learn from the past and predict the future,
Exactly.
not just regurgitate what they've seen before.
That's the goal. But there's a flip side to this:
Yeah.
overfitting.
Overfitting, right?
Yeah.
That's when a model learns the training data too well
Right.
and doesn't generalize well to new data.
It gets too focused on the specifics of the training data.
Almost like it's memorized the answers instead of understanding the concepts.
Exactly.
Right. Okay.
It's like a student who memorizes the textbook
Right.
but can't think critically or solve novel problems.
Or like that super detailed map that only works for one specific route.
Precisely.
So how do we make sure our deep learning models don't overfit?
There are some clever techniques to combat overfitting.
Like what?
One is called regularization,
Okay.
which adds a penalty to the model's complexity.
Okay.
It encourages the model to learn simpler, more generalizable representations.
Okay.
Think of it like a teacher encouraging students
Okay.
to focus on the key concepts rather than memorizing every detail.
So it's like simplifying the map so it's more useful for general navigation.
Exactly.
Okay, got it.
And then there's dropout, which is a really interesting technique
Okay, dropout.
where we randomly drop out some of the units in the network during training.
Dropping out units.
Yeah, it sounds counterintuitive, right?
It does. Why would we want to do that?
It might seem strange,
Yeah.
but it actually forces the network to learn more robust representations.
Okay.
It's like a student who has to miss class occasionally
Mm-hmm.
and has to learn to adapt and rely on their understanding of the material,
Okay.
not just their notes.
So it's like making the model more adaptable
Exactly.
and less reliant on any single piece of information.
And these techniques are crucial for preventing overfitting
Okay.
and improving the generalization ability of deep learning models.
Okay.
It's all about finding the right balance
Right?
between learning from the data
Yeah.
and being able to apply that knowledge to new situations.
That's a great point. It's like finding the sweet spot between memorization and true understanding.
Exactly. And speaking of finding the sweet spot, we need to talk about optimization.
Optimization. Now, that's a word I've been hearing a lot
That's a big one.
in the context of deep learning.
It's everywhere in deep learning.
So what's the big deal with optimization?
Optimization is all about finding the best set of parameters for your deep learning model,
Okay.
the settings that will allow it to perform at its best.
So it's like fine-tuning the engine of a car
Yeah,
to get the most power and efficiency.
exactly.
Oh,
Or like finding the perfect ingredients and baking times for a delicious cake.
right, right.
Those are great analogies.
Finding that sweet spot.
And just like with Tuning an engine or perfecting a recipe,
Yeah.
there's a lot of science and a bit of art involved
Okay.
in finding the optimal settings for a deep learning model.
Okay.
And there are many different optimization algorithms out there,
Okay.
each with its own strengths and weaknesses.
So it's like having a toolbox
Exactly.
full of different wrenches and screwdrivers.
Each designed for a specific task.
And one of the most popular and powerful tools in that toolbox
Yeah, one of the favorites.
is stochastic gradient descent.
Stochastic gradient descent, or SGD for short.
SGD. Okay, that sounds a bit intimidating.
It's a mouthful,
Yeah.
but the idea is actually pretty simple.
Okay, so what is it?
It's one of the most popular optimization algorithms for deep learning,
Okay.
and it's based on a pretty simple idea,
Hmm.
taking small steps in the right direction.
Okay.
We calculate how much each parameter contributes to the error,
Mhm.
and then adjust it slightly to reduce that error.
Okay.
It's like driving towards a destination by making small adjustments to the steering wheel.
So it's an iterative process of
Exactly.
making small improvements over time until you reach the goal.
And this iterative process can be very effective at training deep learning models,
Okay.
especially when combined with some of those techniques we talked about earlier,
Right.
like momentum and careful initialization.
So it's like having a navigation system
Yeah.
that guides us towards our goal.
And momentum gives us an extra boost to overcome obstacles along the way.
I like that analogy.
The good one.
And there are even more advanced optimization algorithms.
Oh, yeah, there are a lot of them.
Like what?
Like Atom, which can help us find the optimal parameters even faster.
So it's like having a supercharged navigation system.
Exactly, with all the bells and whistles.
And these optimization algorithms are essential
Absolutely crucial.
for unlocking the power of deep learning
Without them, we'd be lost.
and getting the most out of these complex models.
It's amazing how much thought and ingenuity has gone into developing these algorithms.
It really is.
And there's another key algorithm that we need to talk about, backpropagation.
Backpropagation, right?
That's one.
I remember that from earlier.
It's a big one.
It's about how the model learns from its mistakes, right?
Exactly. Backpropagation is the algorithm that allows us to calculate how much each parameter
Okay.
in the network contributes to the overall error.
Okay.
It's like having a feedback mechanism that tells us how to adjust our course.
So it's like figuring out which knobs to tweak and by how much to improve the performance of the model.
Precisely.
Okay.
Backpropagation is the backbone of deep learning.
Okay.
It allows us to train these complex models efficiently and effectively.
It's like having a map that shows us the shortest path to our destination.
Exactly.
Okay.
And this brings us to another important component of deep learning models. Activation functions.
Activation functions, right?
Yeah, those are important.
Those are the mathematical functions that determine how each node in the network responds to its input, right?
You're right.
Okay.
They're like filters that determine which information gets passed along
Okay.
to the next layer in the network.
Okay.
And the important thing about activation functions is that they introduce nonlinearity into the model,
Okay.
which allows it to learn complex relationships.
Nonlinearity.
Yeah, remember we talked about that earlier.
Remind me why that's so important.
It's what allows the model to capture the intricate patterns and dependencies
Okay.
that exist in real-world data.
Okay.
Think about it like adding curves and bends to our map,
Uh-huh.
making it more realistic and able to represent the actual terrain more accurately.
So without nonlinearity, our models would be stuck in a flat, simplistic world.
Exactly. And there are many different types of activation functions,
Okay.
each with its own properties and best use cases.
It's like having different types of roads for different types of terrain.
Yeah, that's a good analogy.
So it's about choosing the right tool for the job,
Right.
just like with those optimization algorithms we talked about earlier.
Exactly. And finding the right activation function is crucial
Okay.
for building successful deep learning models.
This is all starting to come together.
And all connected.
We've covered so much ground.
It's a lot to take in.
The building blocks of deep learning,
The fundamentals,
the optimization techniques,
the tools of the trade.
and even some of the key concepts like representation learning and generalization.
It's a lot, but it's all important.
It feels like we've really gotten a solid grasp of the foundations.
Yeah, I think we've laid a good foundation.
So what's next on our deep learning adventure?
Well, we've talked a lot about supervised learning,
Supervised learning.
where we give the model labeled data,
Right.
and it learns to map inputs to outputs.
Okay.
But there's another fascinating realm
Okay.
called unsupervised learning,
Unsupervised learning. What's that?
where we let the models loose on data without those explicit labels.
So no labels.
That's like giving them a giant puzzle and seeing what patterns they can discover on their own.
That sounds really intriguing
It is.
and challenging.
Yeah, it can.
And how do these models even know where to begin if they don't have labels to guide them?
It is challenging,
Yeah.
but also incredibly powerful.
Okay.
Unsupervised learning is all about finding hidden structure, clusters, and representations in data
Okay.
without being told what to look for.
So they're just exploring the data.
Think of it like sorting a bag of marbles by color
Okay.
without knowing how many colors there are or what they look like beforehand.
So the model has to figure out its own categories and groupings.
Exactly. One common approach is clustering,
Clustering.
where the model tries to group similar data points together based on various measures of similarity.
Okay.
It's like those online music recommendation algorithms
Uh-huh.
that group songs together based on shared characteristics,
Right.
even though no one explicitly labeled them as belonging to specific genres.
So it's like finding those hidden connections and relationships
That we're-
that we might not even be aware of.
That's the beauty of unsupervised learning.
Okay.
It can reveal insights and patterns
Right.
that would be difficult or impossible to discover through manual analysis.
Okay, and there are techniques for doing this, right?
There are some really interesting techniques for doing this,
Like what?
like those autoencoders you mentioned earlier.
Autoencoders, right.
They sounded really interesting,
They did.
but I didn't quite grasp how they worked.
Yeah. Can you explain a bit more?
Absolutely.
Okay.
Autoencoders are a special type of neural network
Okay.
that learns to create compressed representations of the data.
Okay. Compressed representations.
Think of it like compressing a large image file without losing too much quality.
So it's like finding a more efficient way to represent the same information.
Autoencoders work by first learning to encode the data
Okay.
into a lower dimensional representation called the latent space,
Latent space.
and then decoding it back to its original form.
Okay.
The magic happens in that latent space,
Okay.
where the model captures the most important features of the data
Okay.
while discarding irrelevant noise.
So it's like boiling down the data
Yeah.
to its essence.
Exactly.
Keeping only the most meaningful bits.
And this compressed representation
Mhm.
can be incredibly useful for a variety of tasks,
Like what?
like anomaly detection,
Okay.
where you're trying to find data points that don't fit the usual patterns.
Okay.
Denoising,
Mm-hmm.
where you're trying to clean up corrupted data
Okay.
and even generating new data that's similar to the training set.
Hold on. Generating new data? Didn't we talk about that with Jans?
Catching on quickly.
Can autoencoders do that too?
While standard autoencoders are primarily used for compressing and reconstructing data,
Okay.
there's a special type called variational autoencoders, or VAEs,
VAEs. Okay.
that are specifically designed for generating new data.
Okay. VAEs. Tell me more.
VAEs take the idea of autoencoders a step further
Okay.
by adding a probabilistic element to the latent space.
Okay.
Instead of just encoding the data as a single point,
Okay.
they represent it as a probability distribution.
Okay.
It's like saying, this data point is probably around here, but it could also be a little bit over there.
So it's like adding a bit of fuzziness or uncertainty to the representation,
Exactly.
allowing for more variation.
This probabilistic approach makes VAEs really powerful for generating new data
Okay.
that's similar to the training set, but not identical.
Interesting.
It's like having a model that can imagine new variations on a theme,
Right.
like creating a new song in the style of a particular artist.
That's incredible.
That's pretty cool.
So we've got clustering, autoencoders, VAEs, a whole arsenal of unsupervised learning techniques.
As a whole toolbox.
But why is unsupervised learning so important, especially now that we have access to so much labeled data for training?
That's a great question.
Yeah.
It's true that labeled data is incredibly valuable,
Yeah.
but it can be expensive and time-consuming to obtain.
Right.
Unsupervised learning offers a way to tap into the vast amounts of unlabeled data
Okay.
that exist in the world.
It's like finding hidden treasure that no one knew was there.
Exactly.
Okay.
Unsupervised learning can help us discover new insights,
Right.
generate new ideas, and even solve problems we haven't even thought of yet.
It's a powerful tool for exploration and discovery.
Absolutely.
Wow, this deep dive has been an incredible journey.
It's been a lot of fun.
We've explored the building blocks of deep learning,
The fundamentals,
the optimization techniques,
the tricks of the trade,
the specialized architectures like CNNs and RNNs,
all the cool models.
and even ventured into the uncharted territory of unsupervised learning.
We covered a lot of ground.
What stood out to you the most?
For me, it's the sheer versatility of these models.
Okay.
From image recognition to language translation to data generation,
Right.
deep learning is tackling an incredibly diverse set of challenges
Yeah.
with remarkable success.
It really is amazing.
It's a field that's constantly evolving, always pushing the boundaries of what's possible.
And what's most exciting is that we're still in the early days of this technological revolution.
It's still early days.
Who knows what incredible breakthroughs await us in the years to come?
That's the exciting part.
What are you most eager to see deep learning accomplish?
The possibilities are mind-boggling.
Yeah.
Personalized medicine tailored to an individual's genetic makeup.
Wow.
Intelligent robots that can assist us in our daily lives.
Okay.
Even a deeper understanding of our own brains.
That would be amazing.
Deep learning has the potential to reshape countless industries and aspects of human life.
It's both thrilling and a little bit daunting
It is, yeah.
to think about the potential impact of this technology.
It's powerful stuff.
As we continue to empower these models,
Yeah,
we need to be mindful of the ethical implications
absolutely.
and ensure that deep learning is used responsibly for the benefit of humanity.
Well said.
It's a powerful tool that requires careful consideration and guidance.
Couldn't agree more.
But the potential benefits are immense, and I'm incredibly optimistic about the future of deep learning.
I am too. It's an exciting time to be in this field.
This deep dive has given us so much to think about.
I hope so.
To our listeners out there, what sparked your curiosity? What aspect of deep learning are you going to explore next? We'd love to hear from you. Until next time, keep diving deep.